What we're doing is a creative process. So we definitely search for those times or those occasions where you can make your code feel a little bit like art.
New frameworks, new standards. Things are changing so fast, and you're always learning. That makes me happy.
For me, it was really fascinating when I discovered what programming actually is. When you make up an algorithm in your mind, you could execute it yourself with pen and paper or just by thinking hard. This is truly exciting.
It's really creative. Once you get the hang of it, you can create so many different ideas. It's really impacting the real world.
Every software is an artistic project. Since the first day I saw a line of code, I fell in love with Java programming. It's something on which I love so much.
I'm not sure if I've lost myself in coding or it's who I've always been. Coding definitely is going to get you once you type your first successful LOL. You can do and undo whatever you want, and it makes me want to do more. Obviously, I sleep less, I code more, and I'm delighted when every time my customers say they're happy.
It's a very creative activity. If you ask an artist or a singer, why do you sing, or a musician, why do you write music? For me, I'm an artist, I'm a musician of my profession.
One way of looking at it is that code is another form of communication. With Solid Pi, the goal is to explore the potential for code with music. Can we get anybody, not just musicians, everybody making some kind of crazy beats and sounds by writing simple lines of code?
Once you get your code run, the feeling is awesome. You can achieve anything within your imaginary with coding.
That's why I wanted to code in the first place. Create something brand new that hasn't been seen before.
Having imagination to build something beautiful and efficient, beautiful and usable. It's freedom.
Please welcome George Saab.
Good morning. Welcome to Oracle Code 1. This week, you'll have the opportunity to experience a wide range of technology and, of course, true to our roots, plenty of in-depth Java content. You'll have the chance to hear from Java experts such as Stuart Marks, Poonam Parhar, Jim Manico, Venkat Subramaniam, and many other Java luminaries. Sessions are filling fast, so make sure you've downloaded the Oracle Events app and register for the sessions that you're interested in. We're going to have many more activities throughout the week, and of course, the always popular hallway track where you can meet old friends and make some new ones. Please also check out the Groundbreaker Hub and thank all of our sponsors. Code 1 is all about expanding our horizons and learning new things. Our invited speaker this morning is going to talk with us about a technology that most of us have probably heard of, but maybe not all had a chance to dig into and really understand. She has conducted research at Harvard and MIT, and is currently a Knight Hennessy Scholar at Stanford, specializing in quantum computing. Now, if I were to list all of the awards that she has received, we'd be here all morning. So instead of that, without further ado, please help me welcome Jessica Pointing.
Raise your hand if during your trip here to San Francisco, you have visited Stanford or you intend to go visit it. Okay, more than I expected. Well, if you've ever been to Stanford, you would notice that the campus is pretty large. And so a lot of people ride a bike to get around. And there are some bike sales. And actually, that's where I got this bike. I got this electric bike at a bike sale for just $35. It was a pretty good deal. And as you can see, it's an electric bike. The only problem is it's missing its battery. So it rides just like a normal bike. And one day, I'm riding up a hill on this bike, and a guy sees me, and he assumes that I'm riding an electric bike. And he asks me, how come you're struggling to go up that hill? And I tell him why. But perhaps you have had a similar situation. You've struggled to go up a hill on a bike, and you know it can take you significantly longer to get from point A to point B, your final destination. Well, imagine that computers are like this. We start off with some initial state, point A, and we want to get to some final destination, which can be solving a problem, maybe in machine learning, or in chemistry simulations, or in financial modeling. And the path to get there can be difficult, and it can take our computers a really long time to solve certain types of problems. It could take days or months or even years. Well, quantum computers could change that. A quantum computer is a fundamentally new type of computer that could help us solve certain types of problems significantly faster. You can think of a quantum computer like an electric bike with a battery. It has an extra power, an extra boost that allows us to solve, in particular, difficult problems faster. So this brings up a few interesting questions. One is, what problems could we solve faster with quantum computers? Two is, what is the equivalent of the battery in the quantum computer? We know in an electric bike, the battery gives it its boost, but what exactly gives the quantum computer that advantage? And three, what is the current state of quantum computing? Can you code on one? Can you use one? And we'll explore all of these questions in this talk. So first of all, what problems can we solve faster? Well, because a quantum computer is a fundamentally new type of computer, we actually can't solve all problems faster. We actually have to figure out which problems can we solve faster. And some researchers have already done this. So let's take a look at an example. Let's say I give your computer the number 15, and I say, find me the two numbers you must multiply to give 15. Well, that's extremely easy. Your computer knows 5 and 3 multiply to give 15. But what happens if I give it a 617-digit number? And I say, now find me the two numbers. Well, your computer is not going to be able to handle that. And in fact, it could take up to 1 billion years using the best known algorithms on our current computers to find those two numbers. But what about a quantum computer? And when I say current computers, I refer to them as classical computers. And this is just the term for any computer that is not a quantum computer. So in a classical computer, you could do it in 1 billion years. But what about a quantum computer? How long do you think it could take? And I actually want to see what you guys think. So you can go to this poll at polev.com/quantum225, or you could text. And I want to see what you think. How long do you think you could find those two numbers on a quantum computer? And I'm going to give you a few seconds, and then we'll see what you think. Okay. Ooh, okay, interesting. So you guys know your stuff. Maybe. So the correct answer is 100 seconds. And that is pretty fast, right? From 1 billion years to just 100 seconds. And this is the power. Now the answers are going down. But this is the power of quantum computers. And how are we able to do this? Well, that's because researchers have created quantum algorithms. Quantum algorithms are a set of instructions that you give to a quantum computer. And Peter Shor, who is actually a professor at MIT, created a quantum algorithm called Shor's algorithm. And using the mathematics of quantum computing, he showed that it could be faster than any of our current classical algorithms to do that problem. Now you may think, okay, multiplying two numbers, is that an important problem? Well, yes. If you're familiar with cryptography and encryption, you know that this is actually what keeps your internet data secure, the fact that it's such a hard problem on our current computers. You could think of those two numbers as the key to a lock. So as long as no one can solve it in 1 billion years, the lock is closed, and your credit card information, your bank information online is secure. But with quantum computers, if you do it in just 100 seconds, you basically have the key to the lock, and you could break a lot of encryption methods. So a lot of people are worrying about this, understandably. But do we need to worry? Well, first of all, in order to do this, you need to have a large quantum computer, an ideal quantum computer. And currently, no one has built that yet. So no one is going and breaking all your encryption methods. But the second thing is that people are coming up with things called post-quantum cryptography. And these will be methods that will be safe against quantum computers. But actually, that's still in its research stage. And you can think, if we need to replace all of our encryption systems, that could take quite a long time. So it is actually an important problem to think about and to start doing work on. But we don't need to completely worry that the internet's going to blow up anytime soon. So we've seen that quantum computing can be applied to security. What about another application? Well, actually, one of the first motivations for quantum computing was to be able to understand nature, to simulate atoms and molecules. And because atoms and molecules, they all follow the laws of quantum physics. Quantum physics describes how the world works at the level of atoms and subatomic particles such as electrons. You can understand its behavior. So it makes sense that we'd want to use a quantum computer, which is a quantum system, to simulate nature, which is also a quantum system. So if we could simulate these molecules and atoms, what sort of applications could that have? Well, one is in medicine. When you want to design new drugs, you want to understand how these molecules interact with the molecules in our body. And so if we could simulate that more accurately on a computer, on a quantum computer, then we could potentially discover new medicines. Well, how about materials? Materials are made up of molecules. So again, if you could understand how these molecules behave and give rise to new properties, then we could potentially design new materials that can make the devices you use, like on your phone, better. So far, we've seen that quantum computing could be applied to security and chemistry simulations or physics simulations. And actually, we know that quantum computers could solve these problems exponentially faster. Now, what exactly does that mean? Well, let's say I give you your phone, and I say, now enter your passcode. But now you only have one digit. Well, that would be completely useless, because you could just solve that in 10 tries. But now, what happens if I add 4 digits? And actually, the iPhone used to be like this. Well, that would actually be harder. Now it would take 10,000 tries. And now you have to enter 6 digits. And the security is even more. Now it takes up to 1 million tries. This is what the problem looks like. Even though the size of the problem increases in a small amount, the time to solve it scales exponentially. And quantum computers, for certain these types of problems, could give us this. You could see that as the size of the problem increases, it doesn't scale for the time to solve it. And that is the power of quantum computing. Now, I can't be at a software conference without mentioning machine learning and AI, but we all know that we've made more progress in AI now because of the more powerful computers we have today compared to many years ago. And in a similar way, people think that quantum computers could also help advance artificial intelligence, and we could apply it to machine learning. And actually, if you look under the hood of machine learning and quantum computing, it's very similar. Machine learning, the mathematics of it all, is a bunch of vectors and matrices. And actually, quantum computing is also a bunch of vectors and matrices. So you can actually naturally map the two together. And this is a field called quantum machine learning, and a lot of people are doing this. Another application is called unstructured search. And to illustrate this, I have a bag with 100 balls. Now let's say I ask your computer, find me the ball number 3 in this unstructured bag of balls. Well, what does your computer have to do? Since there's no structure, it has to pick up a ball, check whether it's the number 3, pick up the next one, and continue until it finds the number. So this could take up to 100 tries, because you could pick 3 on your last try. But what about a quantum computer? How long do you think it could take on a quantum computer? It could actually take just 8 tries. And again, we can do this using a quantum algorithm. And we can generalize it. So on a classical computer, it would take up to n tries. But on a quantum computer, it would take up to square root of n tries. And this is using a quantum algorithm called Grover's algorithm. And later in this talk, we'll see actually how you can implement this algorithm on a quantum computer. So we've seen some really interesting applications: factoring, simulations, machine learning, and search. And these are so general or broad enough that they could be applied to industries. such as artificial intelligence, medicine, materials. And people are even trying to do it more to other industries, such as finance, space, logistics, and scheduling. So as you can see, quantum computing has all of these potential applications. In summary, we could solve the unsolved problems. Something that could take 1 billion years, we could solve in just seconds. And that's what's exciting. So now you may ask, okay, so how are we able to do this? What is the equivalent of the battery in the quantum computer that gives it the boost to solve these problems faster? Well, the short answer is quantum physics. And as I said, this describes how atoms and subatomic particles such as electrons, how they behave. And there are many quantum effects. And we'll focus on one of them in this talk today, called superposition. So what exactly is superposition, and why does that give you a boost? Well, to understand that, let's understand how computers work. We know that computers, they have bits, zeros and ones, and any character can be represented as a sequence of bits. So here, to illustrate this, I have a donut. And let's say the plain side is equivalent to 0, and the frosted side is equivalent to 1. So what about a quantum bit? What would that look like? Well, when a quantum bit is in superposition, it can actually be 0 and 1. It could be a combination of 0 and 1. And you can think of it like a spinning donut. If I ask you, is it 0 or 1? You can't tell. So why does that give us the power? Well, let's say I give you a box, and there are 2 donuts inside. And you open up the box, and I ask you, what combination do you see? Either you'll see 0, 0, which is equivalent to 0, 0, 0, 1, 1, 0, or you'll see 1, 1. But now, if you open up the box, and there are 2 quantum bits spinning, you say, well, I see all of the combinations at the same time. And that is the power of quantum computing. You can actually be in multiple combinations, multiple states at the same time. And what power does that give us? Well, that means that when we're doing the computation, we can process these multiple states of bits simultaneously. And so now I have another question for you. How many combinations will there be if you had 300 qubits in superposition? Let's see what you guys think. Okay, interesting. All right, so the answer is 10 to the power of 90. So why is that? Now the answer is go. But actually, 10 to the power of 90 is an insane number. That's 1 with 90 zeros after it. That's more than the number of atoms there are in the observable universe. And why was it 10 to the power of 90? Well, as I said, if you have n qubits, you can be in 2 to the power of n states. So 2 to the power of 300 is roughly 10 to the power of 90. So this is the power of quantum computing. Now you may ask, so how does it actually work? How does a quantum computer operate? Well, let's understand how a normal computer operates. On a normal computer, you have logic gates. You have a 0, you put it through a NOT gate, you end up getting 1. And then we combine these logic gates to make modules, to make chips, circuits, and then you have your computer. Very simplified. Well, in a quantum computer, we have similar things. Instead of logic gates, we call them quantum gates. So we actually have the equivalent of a NOT gate. It's called the X gate. So this says if you have your bit and you put it through the X gate, it ends up flipping it over. Okay, well that's fairly simple. That's what a classical computer can do. But we have another gate called the Hadamard gate. Now this gate puts our qubit into superposition. So it's 0, and then when we put it through the Hadamard gate, it now ends up spinning. And this is one of the powerful effects of quantum computing. And we actually have multiple other gates that do other quantum effects. But what the goal is you can now execute a quantum algorithm with these quantum gates. And the goal of the quantum algorithm is to use these quantum effects in special ways to solve the problem. And so when you combine multiple of these quantum gates together, that's how you can get a boost. So actually, let's revisit one of the algorithms we saw. That is the one with the balls, Grover's algorithm. So to simplify the problem, I'm only going to have 4 balls. But let's say again, you want to find the ball number 3. Well, how do we do that? On a classical computer, it could take up to 4 tries, since you have 4 balls. But on a quantum computer, you could actually do it in just 1 try. Why is that? Well, if we want to execute this on a computer, we have to convert it all to bits. So here's the number, and we convert them to bits. And we want to find the bits 1, 1. So this is the quantum circuit for Grover's search for the case of 4 balls. And what this shows is you have 2 lines, and this corresponds to the 2 qubits. So the top line is the first qubit, the bottom line is the second qubit. And you can see, you've seen these gates. We have the Hadamard gate, we have the X gate, and there are some other special gates that do the other quantum effects. And you've already seen these ones. And the power is that, as you see at the beginning, we put the Hadamard gates on both of the qubits. So that means we're putting it now into superposition, which means that you're processing on all 4 numbers at the same time. And because you can now process at all 4 numbers at the same time, that makes it a lot faster. And then in the end, we actually make something called a measurement. So we end up actually getting classical information at the end, like bits 1, 1. But this is the power of quantum computing. So now that makes you question, what is the current state of quantum computing? I've talked about the applications, I've talked a little bit about how it works, but what can you do with it? So one of the most common questions I get asked when I'm saying I'm working on quantum computing is, when will we have quantum computers? What is your estimate? And my response is, now. We actually have quantum computers. They exist. And that's really exciting, because a few years ago, that wasn't the case. And so a researcher like myself, I can actually run quantum algorithms on a real quantum computer. So then you may ask, can you program a quantum computer? Yes, you can. You can program a quantum computer using quantum gates, such as the one I've shown you. So actually, since this is the Java keynote, let's look how you would do that in Java. So there are a bunch of quantum computing APIs that people have built. And this one is called Strange, and it's a quantum computing API for Java. And actually, I believe the creator of this is watching this on live stream, so hi. But let's see some of the code. And this is taken, and he's actually written a book on quantum computing and Java, and these are some samples taken from the book. So first of all, we're just creating a quantum circuit method. Now, in this case, this is like the syntax of the code, but to basically put it, we're creating a simulator. Now, what do I mean by simulator? Well, the thing is, as I said, quantum computers, underneath the hood, it's all vectors and matrices. So you can actually run a quantum algorithm on a classical computer. And then you may say, well, what's the point of the quantum computer? Well, it would just be a lot slower on a classical computer. That's why we need the quantum computer. But you can simulate it. So here we're creating the simulator. And there are other quantum programming languages that actually let you run it on the real quantum computing hardware. And so then we create a program. So we're just specifying, in this case, 1. And this is the number of qubits. So we have 1 qubit. Then a program is consisting of steps. As you saw in Grover's algorithm, there were the steps of the gates. So we're creating the step. And then we're going to add the gate. We're going to add the Hadamard gate. Remember, that puts our qubit into superposition. And we're applying it on the 0th qubit, which is just the only qubit we have. And then we just basically add the step to the program, and we get our result by running it on the simulator. So you can see that it's actually pretty simple to write code on a quantum computer. Now, the next question I get asked is, how do we build a quantum computer? Well, in order to understand that, we'd have to understand how we build normal computers. Computers are made up of transistors, which act as the zeros and ones by blocking and allowing the flow of electrons. But it actually didn't used to always be that way. They actually used to use vacuum tubes to act as zeros and ones in the old days. But transistors ended up being more scalable, easier to use, and cheaper. So that's why we use them today, and it's taken off. But I bring this analogy because just as there were different ways to build a computer back in the early days, there's actually different ways to build a quantum computer right now. And here are some methods. So you can use superconductors, and the difference in quantum computing and computers is that when you have your bit, instead of just being 1 and 0, it also needs to be able to be in a superposition. And actually also needs to have the other quantum effects. And so all these substrates, we call them, can do all of these things, like put in a superposition and other quantum effects. So we can use superconductors, we can use trapped ions, which are atoms with a net electric charge confined into a space. We can use photons, which is basically light. And you can even use diamonds. And so you can see that there's a lot of interesting ways to build a quantum computer. And right now, the way people are trying to figure out which is the equivalent of the transistor, we're not quite sure yet. But I would say one of the most popular ways is superconductors. A lot of the big companies are working on that. But who knows if that's the equivalent of the transistor or something else. And so actually, I'm curious what you guys think. How many physical quantum bits do you think we have now on a real quantum computer? Let's see. Okay, interesting. All right, so you guys, okay. It's a good range in the middle, I guess. So the correct answer is, it's around 50 to 100 quantum bits. So as you can see, that's something, but it's not like a million, right? And now the answer goes up. But that's how many physical quantum bits we currently have on quantum computing hardware. So you may ask, well, why can't we just build millions of quantum bits on our quantum computers? Well, you could think one of the big challenges is that it's hard to keep the quantum effects. Just like when I'm spinning this donut, eventually it sort of stops spinning, and it loses its spinning. And it's just the same in a quantum computer. The qubits, they eventually lose their superposition. They eventually lose their quantum effects because it's so hard to control them and isolate them from everything else that's happening. And it's even harder when you have multiple qubits together. So it's a real challenge to build a quantum computer because you have to control these atomic particles and make them have all these quantum effects. But despite that, it's really amazing that we've already been able to build a quantum computer. So our current state is around a 50-qubit quantum computer. Now, what is the ultimate goal? The ultimate goal is to get to something called a large-scale quantum computer. This is one with millions of qubits. And as you can see, we're a bit far out. But the reason why we want to get to a large-scale quantum computer is because that is the one that could break your encryption, that could run Shor's algorithm, that could do Grover's search, that could revolutionize a lot of industries because that could unlock a lot of potential problems. We could do a lot of things with a large-scale quantum computer. But in the meantime, that doesn't mean that we can't do interesting things with the quantum computer. There are a lot of intermediate goals. And actually, one of the most immediate intermediate goals is something called quantum advantage. And the idea is that the current quantum computing hardware we have could solve a problem significantly faster than the best classical computers, supercomputers. And in fact, companies right now are working on this problem. They'll take an algorithm, they'll run it on a real quantum computer, and then they'll compare it to the best supercomputers in the world, and they'll see whether the quantum computer is faster. And people think maybe that this could happen in the next few months, if not maybe next couple of years. So this would be pretty exciting. And this could have a potential impact on a lot of industries. So what are people working on, and what else do we need to do in quantum computing? Well, I came up with an acronym called MATHS. So I'm from the UK, so we say maths instead of math in the US. But here is what it means. So M is milestone. So we need to outperform the best classical hardware running the best classical algorithms for a particular problem. This is the milestone of quantum advantage, because this shows that a quantum computer can actually do something that a classical computer, even the best supercomputers, cannot do. And hopefully we could reach this milestone soon. A is applications. We need to continue to create algorithms for useful applications for quantum computers. And in fact, a lot of companies are doing this. There are a lot of quantum computing startups that are working with big companies, and they're asking them, what are the hardest problems you have? And they're figuring out, could a quantum computer help solve that hard problem? T is theory. We need to continue looking at the theoretical basis, the underlying mathematics, and find more problems that are hard to do classically, but easy to do quantumly. H is hardware. We need to continue to increase the number of qubits, but also reduce the error in the quantum gates and qubits. As I mentioned, the error comes about when the qubit loses its superposition and other quantum effects. So it's not just the number of qubits that counts, but also the quality of the qubits. How long can they stay in superposition and maintain their quantum effects? So we need to continue to doing this in the hardware. And S is shift. We need to shift our mindset from the classical realm to the quantum realm. And there's a lot of interesting things that have been done around this, a lot of educational materials. There's a lot of quantum computing hackathons that popped up. In fact, Peter Shor himself, who invented Shor's algorithm, has a paper where he talks about why he thinks there haven't been as many quantum algorithms, because we're not familiar with quantum, and we don't know how to build these quantum algorithms. But there's a lot of exciting ways to educate people about this. And in fact, I started a quantum computing club at Stanford, and we've had workshops where hundreds of students have come to learn about quantum programming. And so we really need to develop the next developers for quantum computers. And so you've seen that on quantum computers, we could solve certain types of problems significantly faster. It could help us understand nature, which could help us in medicine and potentially artificial intelligence. I think there are two future states of the universe. One with a large-scale quantum computer, the one with millions of qubits, and one without a large-scale quantum computer. And right now, we're in a superposition of both. But paradoxically, as researchers, our goal is to break that superposition so that one day we'll have a quantum future. Thank you.